Okay. So everyone, welcome to Multimodal Weekly. This is a virtual webinar series hosted by the team at 12 Labs where I'm working. Some of you who are new, for a little bit context, we've been meeting on a weekly basis, virtually over the past about 2 years or so. As the name suggests, a big focus of the initiative is basically evangelize new research in multimodal AI and foundation models. Big focus of our company is on this space. So super excited to see multimodal AI has been getting a lot more traction over the past 2 years or so, right? Since we get started the list. Besides researcher, we also have um, uh, developers, founders who work on a variety of different like application leveraging video and multimodal in different verticals. We have a Discord community where folks are pretty active in sharing their project they're working on. So oftentimes we have these folks coming in and share their projects. And finally, internal team members and partners talking about how to use a platform and API. These are some samples, recent session in Multimodal Weeklies. As you can see, there's a variety of topics, right? Ranging from like data labeling to video generation to what else over here? New architecture, video editings, um, hallucination in multimodal LLMs, video world modeling, etc. So for today's session, super excited to welcome Quentin Garrido, who is calling from Paris and is currently a research scientist at Meta, the Facebook AI research division. And for the talk, he prepared some presentation on his recent paper, and I believe that the one is the last paper of your PhD program as well, right?
Yes.
Yep, the paper is titled Intuitive Physics Understanding Emerge from Self-Supervised Pretraining on Natural Video. And a little bit of context on this paper, just based on the abstract that Quentin shared with me. The paper investigate the emergence of intuitive physics understanding in general purpose deep neural networks models trained to predict mass regions in natural video. Um, Leveraging the violation of expectation framework, the paper looked at how the video prediction models trained to predict outcomes in a learned representation space can demonstrate understanding of various intuitive physics properties. And overall, like these show that, by jointly learning an abstract representation space, why predicting missing part of sensory input, this is sufficient to acquire a good understanding of intuitive physics. And I think this is like, pretty exciting stuff because it talk about the theoretical component of how to build, high performance video world models, which is what enable a lot of interesting application like in the broader multimodal AI space these days. As you can see with a lot of the video generation company, but also like, on robotics and, other like sense, what to say, like physical AI domain as well, right? So excited to hear more on the details of what you learned from working on this project. And yeah, just a quick logistical note for the attendees. Feel free to send your question in Zoom chat. Ask Quentin going over the slide, and then we'll also have a short interactive Q&A after you finish. With that, I will stop sharing my screen, and yeah, Quentin, feel free to go ahead and get started and appreciate your slide.
Thank you for the introduction and thanks for the invitation. I'm really happy to be here today to present some of my recent work on understanding of intuitive physics in video models, as well as some of our recent developments in our team since then. So to give some motivations, so we're trying to build machines that learn like humans. And in particular, humans acquire an understanding of some physics concept at a young age. For example, object permanence, the fact that objects don't appear out of nowhere. So nothing's going to appear in front of my face suddenly, for example. This is understood at the latest at around 3.5 months old. Shape constancy, the fact that objects don't change shape suddenly. So I'm not going to turn into a triangle right now, for example. This is understood at around 14 months, similarly with walking and etc. So if we want to build models that learn these properties that are so core to the human experience, we need to benchmark them. That's the first step. The issue is that this for us is extremely simple. We've been doing this since we were babies. So for us, it's very natural, but it's surprisingly hard to get models that work well on them. To cite a few of the benchmarks that we're going to use, Some of them, like Grasp, the latest ones, mention that the models generally exhibit performance equivalent to or less than chance across all tests. So they're evaluating big LLMs, and yet they're getting random performance, same as we expect from a random network. So this is a bit disheartening, and all of these models that we're building basically struggle to understand those simple concepts. So how do we measure this understanding? So we have usually pairs of videos for simplicity of a phenomenon happening. So here we have a ball going behind a wall, and then the ball either disappears or reappears. So on the video on the right, we can see the ball disappear. This is not plausible based on object permanence. And so this video is impossible. On this dataset, which is more real world, we are shown a cup with a hole at the bottom at the beginning, and then we're just going to have a pen fall through that cup. So the pen should fall through, as we've seen there is a hole, but in one of the video it does not, so this video is impossible. And so here for us, this is very easy. And if you take a focused human, you can get almost perfect performance on all of these set of these experiments, but models still struggle. So what can we do to measure this understanding? One simple architecture we can use to try to solve this task is to use a multimodal LLM. So these models are great at recognition tasks. We also have a textual interface, so we can communicate with the model to better probe what it's actually doing and understanding. However, to train them, you need a huge amount of compute and data, and the main limitation for me is that video support is often an afterthought. You have an LLM that has been trained on text, and then you have to add video support afterwards. So for example, we could just show one of the videos and ask the model what is happening inside the video. We can ask it with a simple prompt, is this video impossible or not, giving some context, of course, or showing a pair of video to the model, ask it which one of the two is impossible. The nice thing about having pairs of video that I didn't mention before is that it allows us to isolate the physics breaking events. If you go back to this video, the video are identical, sometimes at the pixel level, except for the physical implausibility. So this means that whatever we measure should be correlated with this physical understanding, and spurious correlations are avoided usually. Another type of method we can have would be methods trying to predict the future directly in pixel space. So here we have, let's say, the beginning of a video, we encode it and we decode it, or we just predict directly, basically, the future of the video. This can be, for example, a diffusion model, can be a simple autoregressive model, and is not, for example, a latent diffusion model, which would fall in a category that we will describe later. So this is really, we go pixel to pixel directly. So these methods are trained to predict the future. We can look at the predictions directly. That's also very useful to debug. But the issue is that usually methods trained that way are not very great at recognition tasks. The representation space after the encoder is usually not that great. And they also tend to focus too much on unnecessary details in the reconstructions. So as I mentioned before, these concepts are hard. So what can we do to find a method that can solve them? Our goal will be, in general, to try to build deep learning systems that can learn like humans and exhibit human-like understanding of these intuitive physical concepts. What I believe should be done, and what some of my broader team believe should be done, is to predict in a learned latent space. So the idea is that we will have a video encoder that will take the past and giving us a representation space. And so this representation can be used to solve many downstream tasks, from recognition tasks, action classification, video segmentation, anything. And then we have a predictor, basically a world model in this latent space that will tell us, for example, oh, what is the future of the video? We can then also, we can train this model by comparing to what happened in the real world in the future by encoding it as well. The main limitations of this kind of method is that there is no way to interpret the predictions. We go from abstract vector to abstract vector space so that we cannot really look at. So it's a bit hard to understand what is going on. And this is why we need to have some precise metrics and ways to measure any kind of understanding. So what do we use in our work? So the methods we base our work on is V-JEPA. So V-JEPA is a method that was designed for video representation learning. So it was purely designed to learn good representations to solve in video classification tasks. It was not trained at any point for this future prediction task in its design, which makes this evaluation that we will do on this intuitive physics concept purely zero shot and with as little contamination as possible from the upstream. So in general, we start from a given video here of a dog, and we apply some kind of corruption, a masking strategy that I will detail after. From this, we extract representations, so through an encoder. And then the idea will be, can we predict the missing parts of the video in that representation space? So here we have removed a large chunk of the video, a large part of the dog. So can the model learn to predict what is missing in this presentation space? and then we just minimize the prediction error with a few more details that I will not discuss here necessarily. But the general idea is by doing this prediction task, we will have to learn about what's going on in the video. Here we have masked a large part of the dog. So if we want to predict what is missing in this video, we have to understand what is a dog. And then, for instance, what is a dog, we can say, oh, there's a dog in this masked area. So this is a general intuition and why these methods can be good at learning representations. In practice, what kind of mask do we use? We can use random masking, like in somewhere such as video MAE. We can use triplet in time, so you match one patch through all the time. But here what we use is called multi-block. The idea is that on each frame we'll apply the same mask on each frame. Here, which will be a union of large rectangular blocks, as illustrated here on the right. So we have two rectangular blocks, we take their union, and we mask this on the whole video. The idea by using large blocks instead of like smaller ones, like simple just randomly dropping pixels or patches in our case, is that the models cannot as much rely on local correlations in the video to solve the task. In practice, we have these very large blocks, and we also have a few strategies with smaller ones, which we hope help learn more motion features, as you can learn by just predicting what's going on in the video. This method is great for cognition tasks. It was developed for that, of course. And so, for example, on tasks like kinetics, so action classification or something V2, which is also action classification, but with more of a motion focus. So kinetics 400 would be, for example, what is happening in the video, playing guitar, ironing would be some classes. Something would be more opening something, throwing something, etc. So more motion-based. And we find that these representations learned by this method, the V-JEPA, achieve great performance. However, here we're evaluating just the encoder, this representation extracting part, and we're just throwing away the predictor. So but perhaps what we want to also to explore in our work is, can we turn this predictor into something useful at test time? Can we go from just this masking strategy, predict missing blocks, to just predicting the future at inference without having ever trained on that? And if we do so, did we actually learn to predict the future in a decent way? As an aside, before we dive into our results, so we use V-JEPA in our work, but since then, and a few weeks ago, we released an improved version of it, V-JEPA 2, which is significantly better at recognition tasks by leveraging the same core concepts. It's still this same kind of general architecture with a few details: better data, larger models, longer training, more higher resolution videos, everything, to really push the performance and the boundary of what we can achieve with such models. It's shown great promise at learning role models for robotics manipulation tasks on top of it. So we use our frozen representations, and then from scratch, we're going to learn a world model on top of that. Here in the paper, it's illustrated for manipulation tasks. So here with a robot in the real world grasping a cup. And this gives us representation that can also be a great combined with an LLM, where we achieve a very strong performance on the video understanding tasks, in particular, everything related to motion compared to image-based encoders. This is posterior to our work, so we go back to V-JEPA V1, slightly modified, and we want to see what this predictor that we learn, what this world model can actually do. So as I mentioned before, we have these pairs of video, so the idea will be to use some kind of surprise measurement. So if we go back to the developmental psychology literature, where all of these intuitive physics notions and analysis come from, for a baby, what we would do to measure this understanding is we show them one video, and we will measure how long is the baby staring at the video. The assumption being that if something surprising happens, the baby will stare for longer. And that's what happens in practice. When something physically implausible happens, the babies will look at the scene more longer. In our case, we don't really have a notion of like time spent watching a video for the model. But what we can try to do is measure the prediction error of the model. So this falls into the violation of expectation framework, also from psychology, where we are going to use what the model expects will happen in the future, what is its prediction of the future, and compare it to what actually happens in the real world. So here we start from a shared beginning of the video. So simply the ball going behind the wall, and we are going to predict as a model to predict the future. In pixels, in representation space, it does not really matter here, just predict the future. And then since we have pairs of video, we can compare with the two possible futures, the one where the ball reappears and the one where the ball vanishes. And we can compare how this differs to the prediction of the model. The question is, do we have a lower error for the possible model for the possible video versus the impossible one? If it is the case, we will assume that the model has understood the physical property at end. As you can see, this is a very crude measurement. Vanishes or stays here, the ball, which is not really low-level physics. We're not comparing like the trajectory of the ball or anything, just does it disappear behind its occluder? So this is also related to memory. Do we remember that the ball came behind the object? But yet, this is enough to trick most models. And this benchmark, which was published now 5 or 6 years ago in IntPhys, still stood to this day. In practice, we don't know when something physically breaking happens in the real world. If now, right now, something appeared out of nowhere in front of me, I would be surprised. But I'm constantly processing a stream of data. And so we wanted to do the same for the models. We're not going to tell them at exactly the right time what's happening. We're going to look through the video as a stream of data. So here we take the first 2 frames, for example, and predict the next 1, 2, 3, 4 frames, 2 here. And we're going to encode the video, predict the future compared to what's happening. So here the ball follows its trajectories, goes behind the occluder. This is not very surprising. We know basic physics. And now the ball is not reappearing, where we think it should start to reappear at that point. So now this is a bit more surprising. Now the surprise is maximal because the ball has been behind the wall for a really long time and it should have been visible by then. And then we look at, if we go even further, we have never seen the ball before. We are predicting what happens. Nothing happens. This is correct. We have a model with a memory of a goldfish in general, as most of these video models can process a few seconds at a time. And so here we have a very low surprise. So what we can do is compute the surprise, this prediction error over the impossible video and the possible one, and subtract the two. This gives us a measure of relative surprise over time. We can see it's 0 at the beginning when everything is identical. It goes up after and when the object disappear, and then it goes down when we have never seen the ball. It is not 0 exactly because in one of the video, for example, the ball is still flying. In one, there is nothing. There's some slight differences, but the surprise is dominated by this impossible event. And that is the good thing with using pairs of videos, is that we can isolate only this physical breaking event. As you can probably guess, the prediction error of a model is also very dependent on the complexity of the scene. If I have to predict what's happening, let's say for you in my webcam right now, it's just me continuing speaking. If now you're looking at football match, it's much harder to predict what's happening. And so every video kind of have this baseline surprise, this baseline complexity, and having pairs of video allows us to remove it. Of course, in humans, we don't need pairs of videos, but this is a harder task that we will also study after. What if you only have one single video? Can you still detect these violations? So we can look at a few benchmarks and at this pairwise classification accuracy from the 2 videos, which one is possible, which one is impossible, with datasets InfLevel, GRASP, and InfLevel-lab, which are ranked roughly by order of difficulty. InfLevel is the first one I showed, very simple, very controlled, especially in its design, was very carefully done. GRASP is synthetic but a bit harder, and InfLevel was the one in the real world in a lab setting. So 50% would be chance performance, rolling a dice. Untrained networks can sometimes do slightly higher than chance, so we took 20 randomly initialized networks and just computed their performance. This allows us to account for some biases that can be in the design. For example, in GRASP, in some videos, balls are changing color, but they're always becoming white. So this has a higher pixel value, which might be picked upon as a spurious correlation. And so here, random networks allows us to control for that. We compared to a few video LLMs at the time, so there have been a lot more since then. So here, Gemini 1.5 Pro and Qwen2 via 72B. We have tried newer models and their performance remains very similar. For pixel prediction, we compared to Video MAE, which was just like V-JEPA designed, Video MAE V2 to be exact, which just like V-JEPA was designed for good representations, but also as a decoder to predict pixels, and so we compared to it as well. And of course, V-JEPA V1 here, V-JEPA as a VTUge that we use here. We found that V-JEPA is the only method that can reliably find the impossible video, achieving almost perfect accuracy on IntPhys and achieving non-trivial performance on GRASP and InfLevel. On InfLevel, I will tell the results after, but what's happened, there's a good reason for why this number is a bit lower. It's good to have a global performance on a benchmark, but it's more interesting, in my opinion, to look at what happens for precise properties. Did the model understand better or objects collide with each other, all the way to the right of this plot here? Or on the left, does it understand just that object exists? To study this, we trained 5 V-JEPA bit large models on how to 100 million from scratch, and we compare over the 20 random networks the increase in accuracy. We report here the effect size, so SSG, over these untrained networks. which is very similar to a z-score, so similar to if we have the distribution of random network, how many standard deviations away are we with our model. Higher is better, but everything above 0.5 or 1 can be considered usually a large effect. What we find is that when we have properties measuring object intrinsic properties, so object permanence, an object is here in the scene, continuity, an object teleports, shape constancy, an object changes shapes, we find a significant increase in performance over these random networks. However, when we are measuring something that is more related to interactions between objects, so solidity, can we go through a wall, collisions, what happens when two objects collide with each other, do they move or not, we find a lower, significantly non-significant results. So the accuracy might be slightly higher, but not in a significant way. When we have non-significant results, we cannot conclude that it doesn't understand it, but we can conclude that we don't have any evidence that it does. As sometimes we find that random networks can get almost perfect accuracy due to biases in the data. So when, in this case, we find lower performance, and in some cases, we can explain it by the design. So for example, gravity is maybe a peculiar case. We have a very good understanding on grasp, but a very poor one on InfLevel. So in that case, it's useful to take a look at how we are measuring this understanding. In grasp, we have a ball flying off a cliff. And the impossible case is the ball goes down as a straight line, like if it had infinite mass. And in InfLevel is, does the object go through the cup that I showed before? The issue here is that to solve the task for grasp, you need 0 memory. To solve the task for InfLevel, now you need to remember what happened almost 10 seconds ago when we showed you a cup with a hole. This is a much harder task, and that partially explains why the model fails. So on InfLevel, we find that on object permanence, where we don't need this memory, we get 80% plus accuracy. On these cases where we need a lot of memory, we get random performance. And so this starts to point at like very precise flaws of the model, notably when there's a lack of memory. What happens compared to humans? So we compared two different settings. One where we look at the relative error rate of the model on the test set of IntPhys. So here, before we had a test set where we tune our parameters for inference for the prediction on nets. And now we have a test set and we're just hoping that we can get something that works. So we look at the relative error. So for surprise, do we have a higher surprise over a whole video of impossible videos over possible ones? And on the right, we have an absolute metric. So we have the surprise distributions for possible and impossible ones, and we compute the AURC between those two. We find that compared to humans, so here a mechanical Turk baselines, the model usually performs better than the human. But more interestingly, we find that it has similar failure modes. When we have occlusions, so for example, here all the triangles, so the same properties, but when the impossible event is behind the wall, now the model performs worse, but the human as well, and we find more similar performance. What's very encouraging as well is that even in a single video setting on the IntPhys, we find non-trivial performance where the model performs similarly to humans, even though in some cases we get very low performance, for example, objects teleporting slightly behind the wall. Still, this is a mechanical Turk baseline, which is not necessarily always the best, even with some filtering. Sometimes people are not really focused. And doing these experiments with other PhD students, we can get perfect accuracy if we're focused. So the human baseline here we have is a bottom line, but we can also do much better. So there are some caveats with comparing to humans, but we find that we're getting similar performance, but most interesting information, as performance is always variable, we find similar failure modes as the humans. So why does it work? Why does V-JEPA work and not the rest? So there are a few parameters we can change in the pretraining. The first one being the pretraining data. So pretrain with different data sets, like something V2, which consists mainly of motions. Kinetics 710 here, which is more activities, people playing football, playing basketball, yeah, something like that. And how to 100 million, which is a significantly larger data set, almost 15 years of video. Of YouTube tutorials, people cooking, people braiding their hairs, these kind of videos. And also the full data set, what I call all, which is basically V-JEPA's training data set. So we find that some data sets are better than others, something V2 being notably poor, which is possibly because of its low semantic diversity, but this will require more experiments to debug. And perhaps surprisingly, here YouTube tutorials are the best, so it's maybe the first time that someone learned something useful on YouTube. What we can also do to study the impact of data is now we just take how to 100 million, the biggest data set, for 15 years of data. And we're going to subsample it all the way to only taking 128 hours of this data, less than a week, which is 0.1% of it. So we will look at this data multiple times through trainings, as our training roughly has a length of 30 years of video. So we will have access to 1 week of video that we see in a loop for 30 years. Kind of sounds like torture. And we find that even at this very low data, in this very low data regime, we have a non-trivial performance, and we almost achieve our peak performance with 1.2 thousand hours of video, which would be around a bit less than 8 weeks, a bit more than 8 weeks of video data if we're watching constantly. So this is like very low amounts, even though we see them a lot. So we don't need that much diversity to achieve this strong performance. Similarly, babies at 3.5 months haven't seen a lot of videos, so it's quite encouraging that we don't need to leverage gargantuan amounts of data to get good performance. Other things that might influence performance are the pre-training objective. So I mentioned masking that we use, block masking, but we can also devise other strategies. One being block plus causal masking. The idea will be that you use block masking, but for a few frames at the end of the video, you completely mask them. So in this way, we already have this future prediction task baked in the pre-training, instead of just tweaking the masking strategy at inference time, which might be detrimental to the model. We also compare to random masking, where we just randomly mask patches in the video. So what's fun is that all strategies get a non-trivial understanding, which was very surprising, as all of these have very different performance on recognition tasks. And so that is encouraging, but we find that still block masking is the best strategy here. Perhaps surprisingly, block masking plus causal masking, so already future prediction baked in the pre-training, is performing the worst. Our intuition is just that this is due to a failure of the pre-training, where the task might be too hard or we need to tweak it more. And so the model basically predicts garbage for these last few frames, which will hinder the performance at inference time. However, they all get non-trivial performance, and so this means that the key to our that we've been doing this performance is the prediction in latent space. Data sources are not that important. Pre-training objective is not that important. So now we have only two things left: the size of the model and the prediction in latent space. And for the size, we trained models from a vid base to a vid huge, so from 100 million parameters to 800 million parameters here. And we find that they all get similar performance with some variation, of course. So bigger models are better, but 115 million, not 80, is enough here. So we have a video model. So this is good because it means that a representation prediction is really the key to everything that was unlocked by the model. It's not an implementation detail from V-JEPA. It's just this general idea of learning a latent space and predicting in it. So this is quite interesting from a more scientific point of view, as it has often been thought that some of these capacities are baked in, are innate in humans. But here we show that a purely learning-based mechanism based on just predicting missing sensory input, which is akin to theories like predictive coding or the free energy principle, are enough to learn to develop this understanding, which I found quite interesting at the time. And what's nice is that we're developing frameworks that are getting arguably, of course, closer to babies and how humans learn. How do babies learn? They can look at the world. Like when they're infants, they cannot really interact much. Then they start interacting with the world to learn even more as kids, as adults. That's what we do. And they don't need to speak or read. We don't need text. We don't need anything. Babies just learn by just watching. And also they are young, so they didn't see a lot of data. And so here what we have is that we observe by using just natural videos from the wild, although we can argue that YouTube is a bit created. We do not have, unfortunately, actions in our model. We're basically built an observer. We get a bit of video in, we predict what's happening next, but we cannot really interact with the world. We don't have any need of text data, we just have video data. And just like humans, we don't need to leverage large corpuses of text or even any kind of language to learn these properties. And also, we do not need a gargantuan amount of data. 1 week of video repeated enough is enough. So most importantly, I think, is that latent prediction here is the only framework that we had that shows that we can understand intuitive physics concepts in a non-trivial way. But will this understanding remain unique to V-JEPA? And I don't think so. So I think what is special is this latent space prediction more than V-JEPA itself. We found that the details in the implementation do not seem to matter from just how you mask the data, everything, but really predicting this latent space was key. And I expect that other representation space will work as well. If you use a strong representation space, for example, say Dino V2 features for images, or if you use a very strong VAE for video modeling, video in latent space for more generative modeling purposes, I expect that you can see this understanding emerge as well, and that really this prediction in latent space is the key. But there's one thing special about V-JEPA still, it's not just any other method, is that everything is learned end-to-end. We do not learn an encoder, then train a predictor on top or model on top. We learn everything jointly. And this means that this prediction task also influences what we keep in the representations. And I think that this may still lead to different behaviors. Maybe we can be more efficient, or maybe we'll focus on some other properties that might be more interesting down the line. So while this other model might be able to exhibit this understanding, I think that learning the latent space at the same time as the predictions makes it really suited for this prediction task in general, which can be beneficial. Especially if we start adding action conditioning to this predictor and we start really predicting consequence of actions or predicting in the future doing pre-training. But that's for future work. Nonetheless, the understanding that we developed remains a bit brittle. As the dataset gets less controlled and more realistic, or we add more noise in the data or more complex environment, the performance decreases. It's still non-trivial on all the dataset that we considered, but we need to do better. We want to get at 100% on everything, and we're very far from that still. So let's build a new benchmark. So IntPhys was very controlled, but not too realistic and quite saturated in performance. Grasp is diverse, not too realistic, and is also was designed for LMs, not for models, so we don't really have a nice pairing of videos, even if we can leverage it. And InfLevel-lab is real world and not very diverse. It's just in a lab moving a few objects. So you end up on a lot of these benchmark having thousands of videos, but it's actually just the same video when changing the object, changing the background color, this kind of thing. So the idea that we worked in a subsequent project, benchmark called IntPhys 2, is to kind of get everything at once. It will be a controlled, it will be very controlled, photorealistic by using more modern game engine and assets, with diverse diverse setups for benchmarking the models, more diverse environments. We're not in a lab, we try to go in the real world and design it from the ground up for both LLMs and world models. The general idea that we have is just scaling IntPhys, which that's why it's the name. So here, for example, we still have these pairs of video. So we have a ball rolling down a hill. In one case, we have a small slope, so the object should bounce on it. And we are moving the camera at the same time. So as you can see, the video looks much nicer than IntPhys 1. It's not real, but it's starting to get closer to realism. And then when we have these two videos of these two possible video futures, we just swap the ending. So once the camera is moved and we don't see the slope, we can get the ending from the object not bouncing or not and stitch it to the video where it will be possible or impossible. So in one case, the ball bounces on it and goes up. In one case, it will hit it and go through. And in one case, there will be nothing and the ball rolls. In one case, there is nothing and the ball bounces randomly. Same design choices as in Phase 1, we still have this pair of impossible, possible with only one slight changes, but in a more complex settings. To compare to others, we have a lot more what I call setups, which are like test beds, so a ball rolling or something. Here we have a lot more. We have a lot of experiments, ball rollings, ball teleporting, boxes. We have hot air balloons going up and down to hide objects, to create these occlusions. We test a similar number of properties as other benchmarks. And we have a much more diverse requirement on memory. So I mentioned before that we needed to have this task, to solve this task, you need some kind of memory. If you have an object behind the wall, you need to remember it was there before. And so here we try to have a more uniform distribution of what I call the seconds of occlusion. So how far back in the past do you need to remember to be able to solve the task at all? So some datasets like IntPhys are very low on memory. Grasp doesn't go too far. InfLevel is quite bimodal, but try to have a better coverage. And we also introduced camera movements as a way to create occlusions to get more diversity. So we're just basically trying to take these evaluations and take them out of the lab setup. As you can see on the right for the examples, Grasp, InfLevel, and IntPhys is pretty like lab-like settings and trying to benchmark this in the real world. So what's the good and the bad is that here every method is performing quite poorly on different subsets. So we have four subsets in our data sets: easy, medium, hard, based on the number of occluders, camera movements, complexity of the scene, and also a held out test set, for which we have a leaderboard. So we find that all the methods are performing poorly. V-JEPA is performing non-trivially, but not too high to be considered too significant, even though a lot of these models perform quite well on IntPhys. So we have a lot of work ahead of us to try to match human performance, which is really exciting. Some samples of the dataset, as the videos will be more clear than me describing them. So here we have a hot air balloon on a parking lot going up, and then it will come down and an object will appear or not. So here, object appears, this is impossible. I only will show you impossible videos, and they look a bit nicer without the compression of the video player. So here we are in the Place des Vosges in Paris, and we have a small contraption with a ball rolling on a ramp. And then the ball is like it was stopped by an invisible object. So this is impossible. It should have gone further. And for the last one, we have a ball going down on these rails here on the car tracks. So it will go behind the first occlusion, the first occluder, but it will reappear on the other track, which is impossible, direct teleported. So we try to have some more diverse videos to make it a bit harder and try to go closer to how we perceive these properties. Sure, we are tested in a lab as babies, but as adults, we experience these properties outside of the lab and in the real world. Yeah. And so this points us to what is missing in the models. Why are they failing so much? What is nice is that in these benchmarks, they are very carefully designed, and so we can really pinpoint clear failure modes. The first one is the lack of memory of the models and the poor use of their context. So models need to remember what happened in the past, and if they cannot look back far enough, you need some kind of memory component. Even if the model is able to look far back in the past, in its context, can it actually use its context? If I have a knowledge that goes behind a wall, and I am tasked to predicting in the future, will I actually use this information from 10 seconds ago for my prediction? And usually they do not necessarily do it. Models also need to be more robust to realistic noise. So I talked a bit about this baseline surprise of the scene before. So different scenes have different difficulties, and we expect that this physics breaking event should be a very surprising thing. And so it should not be lower than, let's say, the average noise over the video, which should be more minor because of slight differences. And so the models need to also become more robust to this noise, and the prediction needs to reflect that a lot more. Also, models are not able to handle usually high frame rates or long enough sequences. So when you need 10 seconds of memory, we have to stretch memory. We have to make the model basically see a PowerPoint of very sparse frames compared to humans. And so at some point, it's very hard to get data that make it even solvable for the model's constraints, even as we try to get them to higher frame rates or with longer memory. So these are like areas that need to be worked on: memory in models, using your context carefully, training better models that are more robust to noise, handling high frame rates and everything. And I think a lot of us know that we need to work on that already. And I think this makes it a benchmark that reinforces this, but also gives us a clear test bed for this understanding later on. So what are the main takeaways? So current deep learning approaches are very non-human-like in their learning. They fail at this simple intuitive physics task. And this latent video prediction, this from models in representation space, offers us the first non-trivial performance at these benchmarks, which I think is really exciting. But this understanding was shown in some benchmarks, but it remains quite brittle. And I think we still need new ideas to close the gap with human level understanding and to make sure that models can exhibit this understanding in the real world, just like us. Thank you for listening.
All right, awesome. Thanks a lot, Quentin. It's more than 30 minutes of content, and I'm sure that there's a lot of details and information that folks want to ask. First of all, I want to quickly recap kind of the main messages from the talk. It sounds like some of the key takeaway from this work is like some of the important pre-training tasks, important of pre-training data, important of the encoder size, right? These are important criteria that can have an impact on the performance of the latent prediction components, video prediction components. I know based on some of the benchmark analysis that you've done, you also talk about some of the like limitation, right, around limited memory of the model, the lack of action conditioning of the prediction, and what else over here? From a data standpoint, like I think it would be interesting to study models. I think the second arrow, right, on the slide about how babies learn and how the latent world models is similar to that process, right? It's super interesting. Yeah, that
Interaction aspect.
yeah. Anyway, I think these are like super interesting analysis and insight. Especially this one because it explained how like if you solve video world models, it basically solve like human intelligence to some point because that's how baby learns when child.
It's very related to some theories in cognitive sciences of how humans may be learning and how we're interacting with the world. So I think it's really nice if we can get models that are similar to theories in cognitive science, in neuroscience, and as well that work on these benchmarks in deep learning. I think that's kind of the end goal that we want to achieve.
Yeah. And also I think like the sheer diversity of benchmarking that you did on this paper is very impressive. There's a lot of like different data set and application studies. So I'm sure it's like a very well treasured resources for the community as well. So with that, I want to definitely opening up the floor for the participant to ask question. So I just so if you have any like real-time question, feel free to just unmute themselves and ask Quentin. And in the meantime, there are a couple messages on the chat that I want to quickly surface. So okay, so there's one question from Pranay, like a couple minutes ago. He asked, did you try to induce interpretability as part of the algorithm design and see if you could? Can you take a look at that first messages on the chat, Quentin?
Yeah, just if I can. I can't seem to find the chat on my side.
You can stop sharing the screen as well if you want to. Okay, now click the chat.
I don't see the chat. Maybe it's something. I know there's some weird things with our corporate accounts for chats. Maybe
You
I'm
cannot,
not. Maybe I cannot see it. Yeah.
oh, you cannot see the chat. Pranay, do you just want to ask question live?
Or
Yeah,
otherwise, I
hey
can answer
Quentin.
based on what you read.
It's no problem for me. So I have a feeling that it's something that is always of interest when you're using latent spaces is trying to induce something in the objective to find interpretability. I have a feeling that the latent space here is too large, and that wasn't the focus of this particular paper anyways to do, although it's probably discussed as being cool because it is.
Yeah.
And so yeah, simply like how big is the latent space? Because from that I can get a sense of like whether this is even a feasible thing to do manually. I do hope one day that we'll be able to automate something like this where we hold one neuron or a set of neurons fixed. I mean, I guess we don't hold those, we vary those, and then we hold all the others fixed and see if there's some uh, semantically meaningful to human interpretable features that come out.
Yeah, the latent space is quite large. Like we use regular VIT, so the representation space is almost the same size as the input space. I
Okay,
mean,
yeah.
factor like 2 or 3, depending on the model, but yeah, just regular VIT, so it's quite large. We try to do some analysis trying to see at like measuring the prediction error on like individual patches, but the representation done by V-JEPA are not local enough to get a good measure of like, for example, was there an error where the ball was supposed to appear or not? We could not get this kind of understanding, which I think is due to not good enough like local features in the model. But I think it would be really cool to kind of see. I know it at the frame level it works a bit better, but like as we get like better models, better representations, like with V-JEPA 2 or not, for example, maybe we can get some more like precise understanding of what the model is using to predict, what it's learning, and also like why does it, for example, if it cannot predict well, where exactly in the video. I think that would be really nice to look at and try to get a better understanding.
Yeah, yeah, that's what we did for, ironically, the Facebook deepfake detection challenge, maybe like 5 years ago now. And then what ended up happening was there was a particular failure mode that the first place winner, which they ended up using the exact same model design that we did, except our ensemble model didn't finish running in time. But they had just this one like block that no other like anywhere in the top 10% had, which was specifically to help with it was using a specific algorithm that had just come out like weeks before the midway point of the contest called face x-ray, and it's just a random paper, and it's uncanny how esoteric that both of us like use that additional specific thing in the pipeline. So there was something that was along the lines of like, this is a failure mode, and then here's an algorithm that was able to address that. So thanks for answering.
Thanks for the question.
Yep. There's another question from well, actually, Igor, I saw you turn on the camera. I think you have a question. All right, you want to ask the question?
Yeah, quick question on this surprise definition. I'm checking the article, but I'd like maybe your elaborate answer. Did you try other definition? I see you use L1 metric or something like that to define surprise. Yeah.
Yeah. So for this, so the two parts to the surprise component. There's the one like for each at each sliding window, which we use L1 for. So here using anything will not change the ranking. If you use like L1, L2, it will not change the order, so it's not very important. So I use this as it was the pre-training loss for V-JEPA, but we could use anything else. And then there's the component of how do you aggregate? How from like a video do you get like one value for the plausibility of the whole video? And so here usually we take the average value, which works well when you have these pairs of videos because the parts that are identical cancel out. But for the single video setting, we look at the maximum surprise. So the highest spike in the whole surprise curve. And this works better for like an individual video because it allows us to kind of ignore this average surprise through time. So I think there are some different ways to like aggregate this information that for like for evaluation. And we played with other things, like for example, using a softmax and interpolate, so log some x to interpolate between average and maximum by changing the temperature. But this didn't help at all. Like really, the two extremes of like average and maximum tended to be the best in different settings. So I think there might be still like some ways to improve these metrics and how we measure it. But yeah, that's how we do it in the paper.
Understood. Yeah, surprise has a little bit of singularity moment now. It's it's more like it's very condensed in time. Okay, so maybe should try some play with the delta types of distributions or something like that. But okay.
Possibly, I think there's definitely a lot of things to explore in that. And also,
Yeah.
like when we say surprise, it's more prediction errors. So sometimes, for example, if now there's like a rapid hand movement, impossible to predict, will be surprising but physically plausible. So I think also like how can we like disentangle the components of like prediction error, or like surprise, or just like difficulty to predict but plausible, this kind of thing. And this we didn't really explore much, but I think there's a lot of like things to look at, especially if we start using more this kind of prediction errors in other works and things like that to try to really understand what's going on.
Thanks.
Yep. And there's a question from Nahid earlier about what do you mean by impossible video?
Yeah. So by impossible, we mean a video with a physically breaking event. So it's something that as human, we will not experience in the real world. So of course, when we create them, there's like magic tricks or we use simulators to create them. But it's basically physics that is different from the one of the pre-training distribution. So for us humans, the real world, in our case, YouTube videos, which usually should be a snapshot in general, if it's well curated, of human videos. So this is how we define them. But if you train the model on a distribution of like objects appearing out of nowhere, disappearing, or video games like superhero movies, then the notion of like possible and impossible becomes completely different, and we might expect different behaviors, and then the definitions would not hold anymore. It's really impossible based on natural videos in the real world with the regular laws of physics.
Absolutely. Okay, I don't see any other question on the chat. Oh, just one clarification. This is the work based upon V-JEPA, not V-JEPA 2. Right?
Yes, this was based on V-JEPA with a small modification using raw positional embedding. So it's in between V-JEPA and V-JEPA 2, but it's much closer to V-JEPA and was done before V-JEPA 2, which was released a couple of weeks ago.
Yeah. And also on that note, maybe you have already mentioned, but what is like sort of the measure
What is
advancement between V-JEPA 2 compared to the previous version?
So the main changes are, I think, so these models are quite tricky to train. And so there was a lot of work that went on to the trying to scale the models to larger models, to longer training time, and to bigger data sets of video. So there's a lot of like, say what we could say on the engineering aspects on all of this. So I think that was some of the main contribution, as well as on the how do we use these models. As I think we've gone a bit beyond the linear classification on kinetics and just trying to like see we train the biggest, the best model that we can do. What can we do with it? And so we have all this like LLM alignment, model for robotics afterwards, etc. So I think it's a lot more in like just making this model closer to the real world and like closer to usability in the real world, more than just like a research project scale.
Yep.
So, yeah.
Scaling laws with practical application in diverse.
Basically, yeah.
That's right.
Sorry.
Okay, so there's two new questions here. So from Mike, he wondered if you could use sampling to generate more than one baseline prediction of realistic possible outputs. to address the impossible versus random issue?
Yeah, so I think so in our case we can only the model is fully deterministic, so we cannot generate more video like so there's I think two aspects. Either on the datasets side, we can try to have like different levels of impossibility. So for example, if a ball has a certain speed, we can change the speed at some point as this impossible event and like compare like which was the closest one. So kind of get something that's a bit more continuous. So that's one way on the data side. Also, the model side, if you have a model that can generate different predictions, then maybe like diffusion model or diffusion predictor or something like that, then maybe you can sample multiple predictions and kind of get a better understanding of all the possible predictions of the model and which ones are the closest and the furthest from the real world, which also might be able to encapsulate possible but random events like me moving my arm, for example, which from an observer is not predictable. So I think there's this aspect that we can do both on the data and the model side, and using more predictions will give us like more fine-grained understanding of what's happening.
Okay. And then now I've got another question. Did you use impossible video in the pre-training data set?
So we did. We did not hope. I hope at least. So we pre-trained on like just YouTube videos and like the classical benchmark. So all the pre-training recipe was fixed before we even started evaluating on the benchmark, or even thought we would evaluate on the benchmark. So this should avoid some avoid contamination. And I think it's kind of like humans. We're not trained to like, oh, this is impossible, this is possible. We just see the world and we just learn what is possible. And so in a way, we try to just learn on this data, and all these benchmarks are purely zero-shot evaluation, no single training, even on possible videos, to avoid any kind of issues. So of course, we could train a classifier, possible, impossible, but that's, I think this benchmark is not really, we don't want to like push numbers too far on it just for the sake of pushing numbers. Or we can do like just classifying learning the possible and impossible directly. But we really want to use it as like a unit test of some model that can understand a bit the physical world. So we want to be good without training just for that task and as in as zero-shot way as possible.
Got it. Okay. I don't see any other question. Are there any folks who want to ask question live?
Yeah, I had one that was on did you find or do y'all, I mean there's a lot of people involved in this work, but did y'all have an intuition of fine-grained detail being a failure mode? Because it seems like the architecture, from what I understand about, I think both models is wholly dependent on latent spaces, doesn't use like a hybrid type of okay, for like I would always use a sparse for a hybrid, assuming I would use a sparse rather than dense, but something that captures like that fine grained detail. And then the canonical example for just being canonical and understanding for most people, I think, is like the introduction of those skip connections and units. But I of course, with the model side of this, I guess so. Two questions: did you find or have that intuition that fine grained detail was an issue, and then is that like a future line of work or inquiry to introduce some stuff that has minimal computational increase but captures that fine grained detail? The positional thing that you mentioned actually makes that a little bit more difficult. But yeah, I'll let you take over.
Yeah, I think it's so like the one of the main motivations with this like V-JEPA line of work is to remove these unnecessary or unpredictable details. So by defining your prediction task, we kind of tell the model what should you learn, what should you not learn. And so we hope to remove unpredictable and kind of useless detail as defined arbitrarily. For example, let's say the texture of a cloud or something. But this also means that, I mean, for every model, like details are hard. And if, for example, you have a small object moving, and then if you don't capture this fine-grained detail, you're not gonna be able to track this object or not gonna be able to understand well. And I think that's also why we had this failure with like video MAE, which I mean is not the best, it's not like a very best, like, good like video generator. But since it's like pre-trained like in pixel space, it kind of forgets these details. So there's some struggle on this, and I think that's also where the actions are very interesting. If you could have like action conditioning, that should be really important. Because if you have, for example, let's say you have a small ball moving and you have something like describing its movement or some as an action, then you force the model to capture it. And so I think in that case, that's where it could become interesting to like add this information. So I think it's this fine line between what is fine-grained and useless, but what is fine-grained and useful for a task. And I think it's really how we can define in the prediction task how to keep it or not, to kind of keep this balance. So I think that's both like generative models, or in our case, without a decoder, like trained fully in latent space. I think it's important to be able to capture some of that information. And I think in the benchmarks, that's also why sometimes model fail. It's like too small change in the video that for us as humans is very perceptible that they might not capture as well, or that the distance metrics might not capture as well.
Yeah, thanks. I think super interesting. Thanks. That's insightful also. Yeah, I think training on the usefulness, of course, pros and cons, but yeah, I wasn't thinking about that too much at the when I asked the question. I think there's also a line of doing that additionally well too. So that's cool. Thanks.
Thanks for the question.
Okay.
Maybe a question. There is this physics informed networks, which your approach is not. But in particular, since you observe the 3D world, so Lorentz transformation or any other, like let's call it not trivial, but some simple physics would inform the network much better, so it knows what's the 3D world is, what's the rules of the 3D world. What do you think about this approach?
Yeah, so I think we wanted to go like for a pure learning-based approach. But
Yeah.
previous ones that try to tackle these benchmarks, they use this kind of thing. So this concept as it is of like core knowledge. So I'm not well versed in psychology, so I will just my explanation may be a bit messy. But basically, this idea that we have this kind of almost innate components that allow us to understand the world. For example, like we can segment objects directly. We're just looking at everything of the scene, or maybe object tracking would be baked in. And so some works try to embed that in the model, for example, by using segmentation mask for objects and then object tracking, or even like using a de-renderer on the scene and then tracking the objects with like the physics law that the objects would follow. So this is kind of like the other extreme where you just fully bake in the physics engine for this specific scene. And so this works well as well. But we wanted to go take the other extreme, but maybe there's an in-between. But that's kind of where I think I also see pre-training. Like the pre-training of the model is a way to learn some of these laws. So some might be too hard to learn, so we can maybe bake them in. But in general, I think we'd like to go towards more like learning as much as possible. So overall, I think it's a good way to tackle the problem. But maybe we can just do it with a pure learning way. And in deep learning, usually in the end, that's like the most simple end-to-end approach that tend to scale the best or to work the best. But doesn't mean that the other one is not valid. I think it's a very valid way to solve the problem as well.
Yeah, interesting. Yeah, certainly model learns the physics, okay, in a purely learning manner. Okay, cool.
Great. I think we have pretty much 1 minute over time. So thanks again to the attendees for asking very interesting question. Yeah, appreciate it, Quentin. Thanks for taking your time and answering every question in much details. And
Thank you for the invitation and for everyone to be here. And if you have any questions, just reach out to me offline and I would be happy to chat more.
Yep, for sure. Yeah, I excited to see some of the upcoming work on V-JEPA 2 and other video understanding video world models work from Meta as well.
Definitely, we keep working on that, and there should be things coming out. I mean, we just had a release, so wait a bit, but there will be things coming out in the future, definitely in this direction.
Yep. And for the webinar attendees, recording this session should be available on YouTube within the next 4 to 5 days. So be sure to upload it and share it with you guys who can rewatch it for at your own convenience. Thanks everyone for joining today. And yeah, hope you enjoy the rest of the weekend of folks who are doing outside the US. Yeah.
Thank you.
Cheers.